And hello, welcome back. We're gonna continue our discussion here on the law of the wall. So in the last video, we talked about how do we get this first function. We non-dimensionalized it and we got a function based on the wall functions in the viscous sublayer and the turbulent sublayer. I kind of ignore the intermediate layer because it's extra work and I just want to get a general trend anyway. It's not gonna be that exact. So the idea is to show you, what how this blending function varies as a function of, let's say, y or y plus. So yeah. So the next function is this. Okay, is this function where you have 500 nu c mu over omega star y squared. Okay, so we can do the same things. Okay, so we have y equals to y plus nu over u star. Okay, and omega star equals to this thing here, and then we substitute in. Alright, and we have this form, and we will just copy and paste here as follows. Here one, and here the other one. Okay, so I have a square of this, and oopsie, there we go. And we'll just copy and paste all of this here, and we'll try to apply the square to each term individually. Squared. I'm going to take this out, copy and paste over, and that will be equal to, okay, I'll just cancel out the viscosities, the friction velocities. Alright, and the viscosity should also cancel, so this should be just to the power of 1, and this should come down here, and you can see it's very simple. The identity here. Okay, so moving on, we can start looking at this. So 500 c mu over omega star plus y plus squared. Okay, oopsie, so we can look here. 500 c mu times or divided by y plus squared times omega star plus. There you go. Equals to 500 times 0.09 divided by y plus squared times omega plus. So there we go. And then we can do this. Alright, so in the viscous sublayer, this is practically constant. In the turbulent sublayer, this has a decreasing function with y. Alright, that's the idea. So this is what this function looks like. And if we were to just get this, okay, we just copy and paste here. Okay, we will take a look at how these functions vary. Alright, a scatter plot, yeah. Okay, functions of y plus with respect to y, or y plus. Alright, so these are how these will change. And in the blending function, okay, where's the blending function? The blending function, they ask you to take the maximum of these two values. So okay, oh, looks like they have this beta star over here. Okay, so I should have my c mu over there. Where is it? Okay, this is 500 C, what? Beta star omega star over y. So in effect, this should be C mu here. C mu. Okay. Pardon me for that mistake. And I hope it doesn't mess up the derivation too much. Okay, one here, one here. Okay, here, here. Okay, that's one. Second bit is where? Okay, so these are not omega star. So this C mu should be gone from here. Okay, C mu should be gone. Yeah, this nomenclature kind of confuses me. Alright, so it's 500 over this. There's no C mu over there. Alright. No C mu here. Yep, C mu at the bottom. This one's all the same. And yeah, this one was us trying to derive here. This one is over here. Okay, yeah, these are correct expressions, but I just want them in terms of omega star. Okay. So let's have them in terms of omega star. That's what the CFD code likes to use, so we'll just stick with that. Okay. Omega star. Yeah. Alright. Hopefully that settles it. So C mu should be at the bottom here of the thing. Okay, so times C mu should be at the bottom. C mu. So this should be times 0.09 at the bottom. So I'm just going to pull this across, and the 0.09 at the top should be taken out. Alright. Okay, this looks, I mean the shape's still the same, but it's been shifted by a factor this time. So yeah. Anyway, omega. Yeah, omega plus, I mean the functions are still the same. I just copied and pasted. There's nothing too much there, and everything else should be okay. Yeah. Anyway, so this is what we have, and in the blending function, we are supposed to take the maximum of these. So you can say the maximum of these is maximum of these two is just this line followed by this straight line here. Okay, so max dot dot dot. Okay, equals max of these. Okay, so alright, so it's just a decreasing function, which is fine. Yeah, I will just do this. Alright, and of course if you want to plot it as well, you can put it here. So the max function will be this little yellow curve here. Okay, now I want to put one more function here, and that is which one? The right, this last one. Yes. All right, this last one here. One last function. Okay, this one's a little bit complicated again, but once you put it on the graph, it should be fine. You have this for sigma omega 2 k over c d k omega times y squared. Okay, so this one's a little bit trickier, but we can deal with that as well. So let's try and see where all of this is coming from. Okay, so yeah, for sigma omega 2, yeah, let's deal with the stuff outside first. So for sigma omega 2 over y squared equals to, okay, this is just a constant. K is k plus u star squared. U star squared times k plus. Okay, y squared is on the outside, so I'll have this. Okay, this should be pasting. Yeah, this should go on the outside. Squared, and that's equal to, all right, this here, okay, k plus squared divided by y plus squared, nu squared over u star squared, and then it becomes u star to the fourth. All right, so that's what we get. Okay, so I'll just bring that out. Squared. All right, so that's what we have. Then there's the whole messy thing inside. So let's just write that down. CD k omega equals to maximum of this. Okay, maximum. I'm gonna put a bracket of this, which is, if you take a look at the way this is written, see this 2 rho sigma omega 2 1 over omega blah 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 blah. This is actually this little extra epsilon omega term from the k epsilon equation. You see this here, 1 minus f1 into blah 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 blah, except of course you multiply the density over here, and that's all you're doing. So, and then it seems to be kept. This seems to be kept at 10 to the minus 10. So yeah, let's just do that. Let's try and substitute some real numbers in there. Okay, so I'll get it from the k equation back up here, and get this whole equation here. Rather, I'll get this from here. This is only applies when it's far from the wall, which is fine. This whole equation, and then we go down here, we paste it, and of course we change some of the constants. All right, so it's here. Okay, and then 10 to the minus 10. Right, so this will be, instead of rho sigma omega 2, rho sigma omega 2. So this is the dynamic version of it. But other than that, everything else is the same. So, okay, now question is this. Okay, 1 over omega is pretty easy to do. So we'll have omega star equals to this. So this is omega star actually. All right. Okay. So this is omega star, and then we don't know what this is because this is a divergence summation. Okay, meaning to say there will be, it's actually like that, del omega, del x, del omega, del y, del omega, del z, and that will have a dot product with del k, del x, del k, del y, del k, del z. All right, so that is what that summation, these two actually are. Nevertheless, we can cheat, okay, so to speak. We can cheat to find an estimate in the boundary layer. All right, why can we cheat? It's because in the boundary layer, usually the del by del y terms matter. These terms, the rest of these terms kind of disappear. They are neglected rather. They are neglected. So we can assume in the boundary layer, okay, this actually will just reduce to, okay, just this del by del y here. Okay, all right, so there we are, there we go. And yeah, so this term in the boundary layer, I will just do it like so to make things simple. Okay, so next it's to get all of these replaced. So let's find the expression for y. I'll just copy and paste it here, and then I'll find the expression for k as well. Okay, I'll get the expression for k and the expression for y. And I'll quickly just substitute this in. Non-dimensionalizing. I will get this. Okay, so I'll just substitute omega in here. Okay, substitute omega in here. Substitute y in here. Alright, substitute y in here. And substitute k in here. Alright, and then now I'll just try and get all this to kind of simplify out. So omega star plus, okay, I'll guess, okay, there should be no star here, because that's the omega star already. Alright, so I'll get this out. First it's here. Get these constants out. So it becomes just a del omega star. And I'll get these constant out here as well. One to here. Okay. So this is what we get. Then I'll just repeat here. Alright. And I'll just get this out of here. Alright. So now we can start cancelling everything out. So this will cancel with these two. Okay. And this one will cancel with this. This one will come out here. So I'll just delete this and I'll delete this. Okay. And the new will go to the bottom. So the new squared and I'll have this u star to the 4th outside here. Alright, so that completes our non-dimensionalization for the most part. So you have this 1 divided by omega star plus, then we'll leave it like such. Yep, so we have this, and then we can like substitute this back here into this equation here, or rather into this. Okay, so this, okay, I'll just copy and paste this over. So for this, you can just equate it like the following, equals to all of this times 1 over CD omega CD k omega. All right, this thing I can just get rid of it, and I can just use this here. All right, and then I can just do something to factorize this out. All right, I can factorize out this so that I will have a new square divided by yeah, so there'll be a new squared over u star to the 4th. Okay, and this thing kind of makes it awkward here, this 10 to the 10, but we just live with it, and yeah, and cancel this, this is a del omega plus del y. Let's make it look nicer. All right, and then what is this? How can we non-dimensionalize this? That's always the thing. Can we non-dimensionalize this? Can we non-dimensionalize nu squared over u star to the 4th? I mean, let's see. What are the units? Okay, u star equals square root of tau wall over rho. Okay, all right, so it looks like we could almost do it. Okay, so we have this, and you know, at the wall tau equals to nu partial u partial y, and this we can definitely non-dimensionalize. Okay, so rho nu du dy, so substitute this back, we will get tau over nu. Okay, we're almost there. Whew, it's a lot of work. Okay, anyway, this is 24 minutes. I'll stop here, and then I will continue trying to non-dimensionalize this so that we can somewhat get a semblance of a non-dimensional figure for this at the denominator, and we'll get this density thing out. Okay. Yep. So yeah, thanks for watching. I'll see you guys again. Yeah, I'll see you guys next time. Bye bye.